Hello students, myself Professor Ankur. I welcome everyone for the gate sum session on analog circuits. Today we are going to solve important sums on multistage amplifiers. Let's start with sum session 2 on multistage amplifiers. Let's take a question. This is from the gate 2002 EC paper, and the question is: three identical RC coupled transistor amplifiers are cascaded if each of the amplifier has a frequency response as shown in the figure. The overall frequency response is given in. So there is a figure which gives frequency response of one transistor circuitry. So the gain AV in dB, x-axis frequency, the 3 dB points 20 hertz and 1 kilohertz. So this is basically the lower cutoff and higher cutoff of a single stage RC coupled transistor amplifier. If three amplifiers which are having the same frequency response are connected in cascade, then what will happen to the overall frequency response? So we are given here four options: option A, B, C and D, where if you observe, the graph representation in all the four graphs is actually the same, but the cutoff points are actually different. For the first graph, the cutoff point, lower cutoff is 40 hertz, higher cutoff is 0.5 kilohertz. For graph B, the lower cutoff is 40 hertz and the higher cutoff is 1 kilohertz. For option C, lower cutoff is 40 hertz, higher cutoff is 2 kilohertz. And option D, lower cutoff is 10 hertz and the higher cutoff is 0.5 kilohertz. So now, whenever we talk about cascading of amplifier, the cascade logic will always give you rise in gain, and it will also result in fall of bandwidth. So but obvious, when you see the higher cutoff of the single stage as 1 kilohertz, in the multi-stage logic, the frequency response will have a cutoff which will be less than 1 kilohertz. So from this, you can easily see option C and option B, they will get eliminated, because option C is having a higher cutoff of 1 kilohertz, which is exactly same as the higher cutoff of a single transistor circuitry. And option C is giving you the higher cutoff as 2 kilohertz, which is also not possible, because in either of the cases, the multi-stage amplifier will always have a lower cutoff less than 1 kilohertz. So option B and option C gets eliminated. Now we are left out with option A and option D. So in option A and option D, we need to understand what happens with the lower frequency. The lower frequency will increase in value when we talk about multi-staging, and the higher frequency will decrease in value in the multi-stage. So now if you see option A and option D, the first option A gives a lower of 40 hertz, which is higher than the 20 hertz, and option D, which is actually 10 kilohertz, which is lower than 20 hertz. So as I've said, that whenever we go for multi-staging, the lower cutoff will have a rise in the value and the higher cutoff will have a fall in the value. With that concept, we are left out with option A. So option A has to be right, but let's verify whether we are right or wrong. So here is the logic. The lower circuitry, lower cutoff frequency of the multi-stage circuitry is FLT, which is equal to FL by under root of 2 raised to 1 by n minus 1. And the upper cutoff frequency will be FHT, which is equal to FH into 2 raised to 1 by n minus 1. Here, the value of FL is 20 hertz, FH is 1 kilohertz, and since there are three identical stages, the value of n will be substituted as 3. So on solving, we get the value of FLT as 40 hertz and FHT is 0.5 kilohertz. So the correct answer is option A. So if your observation is sharp, we went for the same solution using concept of logical elimination and we got the same answer from mathematical calculations also. So the correct answer for this question is option A. Next question. This is from the GATE 1996 ECE paper. Let's have a look at this question. The question is, a Darlington stage is shown in figure. So let's have a look at the figure. So this is a Darlington stage shown. If the transconductance of Q1 is GM1 and Q2 is GM2, the overall transconductance GMC is equal to IC of C by VBE of C is given by option A GM1, option B GM2, option C is GM2, option B is 0.5 GM1, and option D is 0.5 GM2. So first of all, what we are trying to relate here is to find the overall transconductance. VBE C is actually the addition of both the VBEs, and ICC is basically the collector current of the second transistor, which is actually IC2. So when we try to find the relation, the first thing we need to figure out is how do you find the value of VBET? I'm notifying the value VBE of C as VBE of T. That is just our notation. So the voltage between the points of base and ground is VBE of C, that is my VBE of T, is basically the incoming current into the incoming impedance. So the incoming current is IB1, and the impedance value measured between the base and the ground point will be R pi 1 plus 1 plus beta times R pi 2. So this is the total value of VB. On similar lines, I can find the value of IC of C, that is my IC2. The value of IC2 is basically beta 2 times IB2. IB2 is as good as emitter current 1, and that is the reason IB2, since it is emitter current 1, will be replaced as 1 plus beta 1 times IB1. Now we just need to take a ratio of both of them. So the value of GM will be IC2 by VBET will be beta 2 into 1 plus beta divided by R pi plus 1 plus beta times R pi 2. The IB1 got cancelled. So now in the denominator, you can eliminate R pi 1 because 1 plus beta R pi is going to be bigger than R pi. So overall, we are left out as beta 2 into 1 plus beta 1 divided by 1 plus beta 1 into R pi 2. So the value comes as beta 2 by R pi 2. So if your observation is sharp, the overall control effect is corresponding to the GM2. So that's the reason the value of GM is going to be same as GM2. So this is the answer. The correct answer for the question is option C, that is GM2.